CalvinFS is an exploration of how to approach two problems simultaneously. The first one is strongly consistent geo-replication of file system state, and the second one is scalable metadata management. These are both really important problems, and each has been addressed before independently. But to our knowledge, they haven't actually been considered together before. Replication across data centers is all about very high availability. There's all sorts of things like squirrels eating fiber cables that can cause major outages. Also, hunters shooting at boxes mounted on telephone poles, plus, boring things like natural disasters. And so some applications have to survive these kinds of hazards. And so the solution is geo-replicate. Geo-replication also reduces read latencies by allowing clients around the globe to perform reads at whatever local data center or whatever data center they're closest to. When designing a geo-replication scheme, strong consistency is necessary for linearizability and serializability. These have become part of the standard set of file system operation semantics expected by users and developers. There are a lot of really, really high-performant storage systems that forego strong consistency. These tend to be really difficult to reason about and have all sorts of surprising and counterintuitive effects that are really difficult to deal with as a developer. And so I would argue that you can't call something a file system if it is not strongly consistent. There are very few pieces of existing infrastructure that actually support geo-replication and export a file system-like interface. There's one that does so via with strong consistency via a variant of Paxos. It's a really successful piece of open source software, and it's a building block in a lot of applications. The system is Zookeeper. You don't really think of it as a file system because for most users, its limitations in scale constrain its role to configuration management. But its success, despite these limitations, really illustrate the importance of and demand for geo-replicated storage mechanisms that have familiar semantics and interfaces. So the second issue is scale. The distributed file systems that use a dedicated memory-resident metadata subsystem, such as ones that follow the Google file system and Hadoop distributed file system models, I'll just refer to these as the HDFS-like file systems for now, because everyone is familiar with that. These have been proven really, really effective at storing very large amounts of data in very small numbers of files. However, putting all of your metadata in the main memory of a single machine introduces a really hard bottleneck on the number of files you can store, obviously, and the amount of metadata update throughput you can handle. If your system is only designed to support MapReduce workloads, this is not such a big problem. If you wanted to use your file system as a general purpose storage for a large organization, this wouldn't really work very well. So there are some systems out there that are kind of in the HDFS-shaped system family that actually do partition metadata across a cluster of servers while keeping the data in memory. They perform their updates to metadata using distributed commit protocols. A really nice example of this is the Ceph file system. There are some others as well. Each of these, however, is still limited to a single data center. So as of when we were building this, HDFS could gracefully handle about 100 million files. We built CalvinFS and spun it up, and on 300 EC2 machines, stored 3 billion files, and there was no particular reason that we couldn't keep scaling it. The number of files was never a bottleneck for us. Our bottleneck was how much it cost to rent EC2 machines for a long time. So each of these problems is important and has been approached on its own. This talk is really about how to tackle them both at once. So I'm going to describe CalvinFS using a bunch of examples because it's really hard just to do it with a whole lot of words. So let's say that you have a directory /home. This is its metadata entry. It contains the full absolute path of the directory, and it has the fact that the directory is a directory as opposed to an ordinary file, which is to say a flat sequence of bytes. And that's the fact that it's a red hexagon. Let's say there are also some subdirectories like home Alex and home Daniel. They get their own metadata entries. The names are embedded directly also in the home metadata entry. So you can run ls home and get a list of all contents of home by reading only the home metadata entry. Let's say that home Alex also has some directory in it and also a flat file in it. Flat files are going to be blue rectangles. The way that this metadata is going to contain a flat sequence of bytes consisting of 2 blocks. The metadata is going to contain embedded information saying that the first 256 bytes appear in block A, and the next 144 bytes appear in block B. These blocks are then going to be stored off elsewhere, not in the metadata subcomponent of the system, but in the data component of the system. Now, what I've described isn't really an architecture for a system. It's just kind of a description of the data that we want to store, and the general which part of the system we want to store each piece of data in. So I'm going to draw the physical placement of this, and we're going to, for now, ignore the upper left part of that and only deal with one directory and one file and 2 blocks. And the blocks are going to stay as these green rectangular prisms. So here's a picture, not of CalvinFS, but more or less of HDFS. The thing at the top, the dark gray rectangle, is the name node, which stores the metadata entries. And then we have a bunch of data block storage nodes that we spray the blocks across. And this is all resident in a single data center, and the outer gray box is supposed to be an illustration of that. Actually, HDFS would also have metadata entries for each block, but we're going to elide that and just say that they're partitioned via a consistent hashing scheme, such that by embedding the globally unique block IDs, in this case A and B, directly in the file metadata entry, the blue box, is enough. So we're not going to actually show the per block metadata entries. In HDFS and also in CalvinFS, all of the metadata is stored in the main memory. For simplicity, let's also say that all blocks in the block store are completely immutable. So if you want to append to a file, you always have to create a brand new block, write your data to it, then append a pointer to that block to the file metadata. This is not really what HDFS does, not really what you would want a real file system to do, but this is what we did just as a proof of concept. So first thing we're going to do to turn this actually into something that looks like CalvinFS is we're going to add another data center, or add multiple more data centers. One of them is falling off the screen because I wanted to just zoom in on 2. What we're going to do is take the data blocks and actually just spray them with the same replication factor across multiple data centers so that each one appears, each data center contains at least one of each block. Now we're going to take the metadata and within the first data center still just partition it across all of the machines. There's not going to be a single name node that's in charge. It's going to be partitioned. Now we're going to take that and we're going to replicate it. And those are going to be replicated the same across all of the data centers. Great, so this is where the data is. It's consistent and we can read it. But now we need to update it and keep it consistent. So for example, let's say we want to create a new file and write to it. I typically practice the monkeys at typewriters approach to writing papers. So let's say I want to echo a keyboard mash to calvinfs.tech or cfs.tech. We're going to break this down into 3 steps. The first one is going to be to write a new block in the block store, and that's going to store the data that we're writing. So let's call it C. It's a globally unique ID. Then we're going to perform 2 built-in primitive metadata operations. The first one is going to be to create an empty file. If there's anything there, it'll be clobbered. This just creates a new empty file with no pointers into the block store. So it's got no bytes. The next thing we're going to do is actually set the first 9 bytes to point to block C. So that does this. So each of these operations we should note, deterministically defines a state transition on the state of the file system's metadata. The outcome and the behavior of the operation depend only on its input, which is logged, which I'll get to in a moment, the input to the operation and the current contents of the metadata subsystem. So to consistently apply this at each data center, what we do is we keep a single global log of operation requests like these. What we do is we insert C, and then we append these to the log. Now every data center has an identical view of this log, because it's global, single object, and they all have the same starting set. So playing the log forward independently at each data center as a sequence of deterministic state transitions on the metadata component will incur no additional cross-data center synchronization. But wait, you might say, if every mutation request is written in a single log that is globally visible, that will be a huge performance bottleneck and a single point of failure. And you're right. So what we actually do is compile large batches of incoming requests and write them out to the handy block store we have lying around. So here we took our requests and edited them to a batch that was being compiled and wrote it out as a block called D. You can tell it's octagonal, therefore it is log entries. We then just append a pointer to a Paxos replicated very small log, which is called the meta log. Now the state of the logical log of operations is just these blocks concatenated in meta log order. This turns out to scale really, really well, albeit at some cost to write latency. So in this particular example, these state transitions were very, very simple. They don't require any communication between metadata servers to figure out what their semantics are at runtime. For example, the write operation that we did, the second one, didn't even look at the directory entry at all. All it did was modify the cfs.tech entry. The create operation did touch both the directory entry because it embedded the name of the file into it, and it also created the file. And these occurred presumably on different machines, although since our partitioning is hash partitioning, so they could have been the same machine. But in the general case, not the same machine. But they didn't really, neither one needed to know the state of the other in order to figure out what to do locally. So let's make things more exciting. Let's check permissions. CalvinFS implements hierarchical access control in the following manner. I skipped this before, but each metadata entry also includes POSIX-style permissions for both itself and all of its ancestors, all of its parent and ancestor directories. Therefore, a given node can tell whether the file creation, the node at which the directory is stored can tell whether the file creation should succeed by looking at whether the user who invoked it has write permissions on that directory, so home Alex in this case. But the other node, the one at which the file is being created, doesn't have that information because the directory isn't stored locally and the file hasn't been created and so that information isn't there. So this ends up being a distributed transaction. There's a data dependency between these nodes. So fortunately, the Calvin execution engine was designed and optimized for OLTP workloads that resemble this use case exactly. The relevant properties here are that the transaction request is expressed as a stored procedure invocation. The order in which it must execute compared to other conflicting transactions is already specified fully in the log. The behavior of the transaction is entirely determined the behavior of the transaction is entirely determined by its logged input and the current state of the metadata store, and its read and write sets are known in advance. The keys of the records that it's reading and writing, which in this case are the just file names, full file paths. So the execution engine Calvin uses the following operations for distributed transactions. I'm going to walk through the same example. So we start by, so here are the two participants that are going in the that are going to execute this transaction. The one on the left stores the directory metadata entry, and the one on the right is where the file metadata entry is going to be written. And we have each participant has some local state about the execution of the transaction. So it proceeds as follows. Each one performs all of the reads that it can locally that have to do with the transaction. We know what they are because we can, by reasoning about the semantics of the transaction, know what its read sets are. So on the left here, we read the directory metadata entry. On the right here, we read, and see there's nothing. So we have an empty read set. So the next thing that they do is they each broadcast their read results to all other participants in the transaction. So now they both have the full set of read results. Now they can independently execute the full logic of the transaction, redundantly, right? So each one is executing the whole transaction, even though they're only physically going to apply part of it. So they each determine that, okay, we're going to rewrite a new, our write set is going to contain a new directory plus the file, and then they write back to their local, in-memory storage, the values that are supposed to have been written out as a result of the transaction. So each participant can actually run multiple transactions concurrently. We use a locking mechanism that ensures that if an operation X precedes an operation Y in the log, then all operations for X that are local to a given node occur at that node before any operations for Y occur at that node. This ends up being sufficient to maintain the invariant that, although transactions may execute concurrently, the outcome is equivalent to a serial execution in log order. There are also a bunch of other things that we have to deal with. All metadata is stored in main memory, but each node periodically snapshots its state to disk. This way a node can recover from a crash by only replaying a tail of the log. Since log replay at recovery time may involve re-executing distributed transactions and therefore performing remote reads, each server needs to be able to serve reads at historical timestamps. Therefore, we end up having to multi-version all data. And then there's a bunch of bookkeeping that we have to do for garbage collection. But multi-versioning is also really useful for another purpose. Fully linearizable reads involve contacting a quorum of data centers. This means at least one wide area network round trip, but clients can perform snapshot reads within specified staleness bounds from any replica with no cross-center communication at all. These can require more thought from developers in situations where applications need to read their own recent writes, but these are still way easier to reason about than asynchronously replicated systems. So what did we trade off to get these behaviors? First of all, writes incurred 3 sequential wide area network round trip times. 1 to replicate file contents in the block store, and then 2 to write to the log. So writes are, the write latency is constrained by the speed of light, which is slow when you're trying to replicate a long way. Second, any operation that involves a single directory or a single file accesses at most 2 metadata entries and therefore at most 2 metadata servers, and the read and write sets are generally known from the input request, so that's fine. But then you have the issue of recursive operations on directories. And these can get really expensive. And these also include any permission change on a directory, even if you're not trying to recursively change the permissions on the children, because all of the children need to know consistently all of their ancestor directories permissions. So the issue for recursive operations is that you don't know the read and write set in advance. So there are a couple of options of things you can do here. The one is to do a dry run of the transaction, see what it would read and write, don't commit it. You don't have to actually do any logging, you don't have to do any isolation for this, you just see what it would do. Note what it read and wrote, and annotate the request and then resubmit it. Now, you can lock the correct things, and if you end up trying to do a read or a write of something you didn't lock because some underlying state changed between the dry run and the actual run, now you just have to restart this. So this works sometimes. It depends on your workload. Another thing you can do is just kind of queue up these recursive operations, and then every once in a while, every few minutes or every user-specified amount of time, shut the system down, apply all of them, and bring the system back up. I appear to have, well, that's okay. So I seem to be out of time. So I'm going to skip the performance numbers, which are it scales. When a data center crashes, everything else keeps going. There's no loss of availability. There's just latency hits when there are enormous failures. So that's kind of a nice property also. So questions, comments, complaints?
Hi, my name is Zhe Zhang. I'm from Cloudera. I wonder if you think like directory rename is even more expensive than other recursive operations like change permission, because you need to change the key of a lot of metadata entries.
Yes. So in fact, the way that we do directory renames is slightly different, because what we do is we have this special permission bit which just kind of completely makes a directory unwritable, regardless of like to anybody, and then makes the copy, and then atomically removes visibility of the old one and creates visibility of the new one. So yes, it is more expensive, but you don't have any additional retry issues.
Okay, so another quick question. So in the example you gave, like writing a file, you write the block first and then like check the permission, create the file. Is there a particular reason why you write the block first? Because I think in HTTPS, for example, we create the file first and then do the block operation.
You could do it that way. This is so when you commit, you want to be able to commit the fact that there is data in the file at the same. Well, okay. In this particular example, I wanted to commit the fact that there was data in the file at the same time as creating the file.
All right. Thank you.
Yeah.
Hi, my name is Brian Bannister. I work at Jump Trading. I had a question about how do you resolve same-time execution conflicts if they, simply like somebody tries to write a file into a directory, but at the same time, somebody in a different location changes the permissions on that directory such that that operation should not be allowed, and you have this latency, but these operations basically occurred at the same time. How do you deal with those kind of conflicts and things?
Well, one of them appears first in the log.
How do you know? I mean, if they basically are executed at, I guess there's, you could still time that out to nanoseconds, so there always will be some operation that was actually first in time. Is that basically the?
Well, they both get, each one gets logged before either of them gets executed. Okay. Right, and so the log is a series of input, just totally logical requests, and the execution has to respect the order that they appear in the log. And our locking mechanism in Calvin handles that.
Okay.